Hello everyone. In this video, we break down the math behind neural network models and explain the basic operations that we have to understand about neural network models. Then in future videos, we will translate this math into practical implementations using popular deep learning libraries, including TensorFlow and Keras. So let's get started. We have seen so far two linear models, one for regression and one for classification problems. In the case of regression, because the output is a continuous real-valued number, we assume that the probability of the output given input features, this x here is a vector that contains all input features, and the weight vector or the parameters that we have comes from a normal distribution with this mean and variance. So here the mean is the dot product or inner product between the input feature vector and the weight vector W. And the noise has a fixed and known variance, which we assume that here is epsilon. In the case of logistic regression, because this is a classification problem, recall that in the most basic form, this y can only take two possible values, 0 or 1. And therefore, we model this probability using a Bernoulli distribution with this parameter where it's a function of w and x. So similarly, because this is a linear model, we have the dot product or inner product between w and x. But because now we need to have a probability value here, a probability score, we use the sigmoid or logistic function. So this sigmoid or logistic function is essential here to make sure that this parameter of Bernoulli distribution is valid, in the sense that this is the probability that y takes on the value 1, and 1 minus this probability is the probability for y equals 0. So this completely defines the logistic regression model for binary classification problems. So if we look at the underlying assumption that we make here is that we assume that the mapping between inputs and outputs is linear, right? And that comes from this dot product or inner product, which basically is a linear combination. So a better idea for solving more complex problems where we have non-linearities or more intricate and complex relationships in the data is to be able to extract some interesting features from the input data using some additional parameters, right? So if I want to put everything in the context of what we have seen, let's say W is this weight vector that we have for solving the linear regression or logistic regression problem, but we don't have to necessarily apply these to exactly the input feature vector. We can actually have multiple layers of transformation and I show this using this spy here, to extract some interesting patterns from this input feature vector X using some other parameters or weights that we have to learn. And this theta here typically refers to the weights or parameters that we have in our neural network model to find hidden representations of data. And this is exactly what we're going to explain in the next slide. So in this case, we want to look at a classification problem where you have three input features, x1, x2, x3. So you can think of these as in the iris flower data set as length and width of different parts of the flower. And then the output here is a single probability, because it's something that we can use a Bernoulli distribution to find the probability that the output is 1, and obviously then we have the probability that the output is equal to 0, right? That was the idea behind the Bernoulli distribution. So let's make this a little bit simpler and break down the math a little bit here. So in this case, what we do, we want to create a network. And the network needs to have these nodes or neurons. So that's why I show here using these circles. And the first part of the network is easy because we just provide the inputs that we have. So here, x1, x2, x3. And I can think of these as one layer, and I call this the input layer. So now the idea is that I want to extract something interesting from this input layer. That was the idea of that phi of x and theta that we just discussed. So let's put one node or neuron in front of this input layer and create these connections or edges. So one thing that is very important here to understand the way that we do indexing here, because this gets a little bit complicated. Since these three sort of like edges or connections that we have, they go to layer one. So this is technically layer one because you can think of the input layer as layer zero if we use Python indexing. Therefore, I use the superscript one with parentheses, right? So this one here, this means that these weights or parameters belong to layer one, meaning that they go to layer one. And then we have two subscripts here. And the reason that we need two here is because each of these connections or edges that you see here, they go from one neuron to another one. Okay. So, and the way I name this is that the first one is the index for the destination neuron. So the destination one has this index one. So you can see all of these, they start with one. And then the second subscript is the index for the source neuron, right? So that's where we start. So this one starts from x1, this one starts from x2, this one is coming from x3. Obviously, you can obviously switch these subscripts, their order, but this is the way that we use in this lecture, where the first one is the index for the destination, the second one is the index for the source. And right now, we're going to do something very similar to what we just saw with the linear models. We're going to find a weighted sum or linear combination, meaning that we're going to multiply this W11 by X1. So you can think of these as X1 going through this connection or edge and gets multiplied by whatever the weight or the strength of this connection is. And the same thing here and the same thing here. And this makes it very easy because you can see that always this second subscript is the same as what we have here, right? Because that's how we define it. W112 means that this is coming from x2 because the second subscript is 2. And very similar to what we did before in the case of linear regression, you can also include this bias term or intercept. And here we also need to make sure that we do the right indexing. So we use 1 as the superscript to say that this belongs to layer 1. And the index or the subscript here that we have, it shows that it goes to this sort of like, neuron 1 in this layer. So you can think of this as having an extra neuron, which is always 1, and that is getting connected to this one. Therefore, we don't really need two indices here, right? Because this is not coming from the actual input features. That's always something that is coming from a fixed or constant neuron, which is always 1. So 1 times B11 is just B11. But here is the main difference between neural networks and the typical linear regression or logistic regression. And the fact that after we find this weighted sum or linear combination, we also feed this to another function, which we call this activation function. And the goal is that this should be a nonlinear function. So can this be a sigmoid or logistic function? Yes, but also there are a lot more options. For example, we're going to see 3-4 more examples of these. And it is very kind of like interesting to know that in many real world cases, you actually don't want to always use logistic or sigmoid functions. So in that sense, you have a lot more flexibility when working with neural network models. So this explains the math behind the operation of each neuron here, right? So once you do the weighted sum and apply this nonlinearity, then you find the value of this node. The other part of this is that now you can have also a lot of flexibility in design by adding more and more neurons, as many as you want, in this layer that we have in front of input layer. And this is what I call the hidden layer, right? Because this is a different way of representing data. And we typically don't know whether this is a good representation or not immediately, but we hope that we find these weights or connections in a way that we find a good representation. So how can we now solve the original problem, which was, solving a binary classification problem? Well, after your hidden layer, you can now have this output layer where we have one node, And this one node is actually like what we did before. You find a weighted sum or linear combination, and then you apply the sigmoid or logistic function. So at the end, you end up with a probability score. And that's the probability that this data point, this input data point, belongs to class 1. And obviously, 1 minus that probability is what we have for the probability that data point belongs to class 0. So you can see that in this case, we only assume that we have one hidden layer, meaning that we get this 3-dimensional data, we convert it to a 2-dimensional data, and then we solve this technically logistic regression problem here. But we can have multiple hidden layers too. Before going through that sort of like part of neural networks, let's just also talk about the operations that we use here and how we can represent them in a compact form. So remember from what we had before that this is the way that we find these the first node in our hidden layer, right? Because we have A11 and A12. So again, the subscript is used to for positioning or indexing within a layer, and the superscript is what shows that these are in the first layer. And so this is, again, something that you can easily write using matrix vector multiplication in general. So let's say you have a vector of all input features, and then you put all these weights that you have here in a row vector. So now you can easily show that this is multiplying this row vector by this column vector, and then adding this constant B11 that you have. And if you want to find all the nodes that you have in that hidden layer, you can also concatenate these furthermore. So now you have this A1, which this is a vector that contains A11 and A12. So here you can have, as many elements as you want, depending on the number of nodes that you have in that hidden layer. And then this weight matrix is what really takes you from this input layer to the hidden layer. And given the way that we do the indexing here, the size of this matrix going from input layer to hidden layer is the number of nodes in the destination layer, which is 2, times the number of nodes in the input layer, which is 3. And you can see this, right? This is 2 by 3 matrix, and you have W11, 1, 2, 1, 3. So all these weights, they go, or connections go to node 1 or A11. And then all these things that they start with 2, they go to A12, right? So that's the most important thing about neural networks, just being able to remember the way that you index or position these weights and inputs. And once you do that, then the rest is very simple and easy to understand. And given this, notation that we have here, now you can see that you can find the entire representation of the hidden layer by simply multiplying this W1, which is 2 by 3, by the input, which is a 3-dimensional vector. And also you need to have this bias vector, which contains B11 and B12, right? So everything now is in terms of vectors and matrices, which is really nice, right? It means that now we can really, avoid for loops and summations and perform things very efficiently, especially when you have access to things such as GPUs, right? That's why, at this point, NVIDIA's GPUs are really revolutionizing AI and neural networks and so on. So going back, to the slides that we have, so you can see that this is kind of like the summary of what we had. So A11 can be written in this form, A12, and we can write this whole thing, right, as multiplying this weight matrix by the input and then adding this bias vector. And now if you want to go from the hidden to the last layer or output layer, so you can do the very same thing here. So you can see that now we have to name these weights. I use the superscript 2 because these things go to hidden layer, or sorry, to layer 2, which is technically our output layer, right? So if I show you here what we have, so you can see that this is our input layer, this is our hidden layer, and then the last layer is what we observe. That's our output layer, right? And since in our output layer, we only have one node or neuron. In that case, we don't really need to have two subscripts, and we can just use one for simplicity. And this only shows the index of the neuron in the sort of like, in the source layer. Right? So 1 means it's connected to the first one, 2 means that it's connected to the second one. We don't need another sort of like index here because all of these, they go only to one node or neuron in the output layer. And this is, again, a simple linear combination and, some non-linearity. Again, I would like to emphasize that this sigma you see here does not always refer to a sigmoid function when we talk about neural networks. But, given that this is in the last layer, this is indeed a sigmoid or logistic function. So that's just something to keep in mind, that we have a lot more choice of non-linearities when you're working with neural networks. And this can be written the same way too. So if you want to know the shape of this matrix, remember that you go from 2 nodes to 1 node. So the size of these should be 1 by 2, right? That's how we define things. And then you multiply this by the input of this layer, which is now this A1 vector, right? Because that's the input. And you need to add the buzz term and find the result of this operation. So this is the idea behind what we call as feed-forward neural networks, right? So the idea is that the information flows from the function being evaluated from X, and X is the input features that we have, and that comes from your data set. So you get the information from the input layer, and then you set these to these intermediate layers, or also known as hidden layers, and finally to the output layer. So if you want to, again, like kind of like, think about what we did in the previous example, you can think of this as a composite function or a nested function where you have your input. You can even apply some pre-processing if you want, and we can show that using this F superscript 1. And then we go through the second layer. That's another function that operates on this result of this f1x. And then whatever we get, we send this to this, third function that we have. And this is technically that our like output layer, right? So neural networks are simply a nested or composite function. And because the data that we have, especially the training data, only contains these inputs that we have X and the outputs, anything in between, we call those hidden layers. And the idea is that if you have more hidden layers, now you can have more complex representation of your data. And with this motivation in mind, that the length of the chain that we have here, or the number of hidden layers, is called the depth of the network, and the dimensionality of hidden layers, or the number of neurons in each hidden layer, we call as the width of the model, right? So we have depth and width. So now to kind of like, make this a little bit more straightforward, let's look at one of the earliest example of neural networks and why they actually matter a lot in terms of solving complex problems. And in order to explain what's happening here, so let's look at something known as exclusive or XOR. So the idea is that if you have two binary values, and I show this by x1 and x2, so each x1 and x2 take on two values, either 0 or 1. So we have 4 possible cases, right? 0, 0, 0, 1, 1, 0, 1, 1. And if you find exclusive or XOR, so that's the notation that we use. So the result is that if there are both zeros or there are both ones, we get 0. And if one of them is 0 and the other one is 1, we get 1. All right, so this is something that is known. You can Google this. It's called exclusive or XOR, right? So if you have these two binary inputs, this is the result of exclusive or on them. So now we can think of this as a classification problem. How? So let's say we have a two-dimensional data set where x1 is either 0 or 1, x2 is either 0 and 1, And you can see that the labels now we have, these results are 2 zeros and 2 ones. Okay. And now let's say you want to define a classifier to separate these two classes, meaning class 0 and class 1. So the issue is that what you really want, you want to be able to have a classifier that gives you this kind of oval shape here. So it says that everything here is 1 and everything outside of this is 0. And here's the problem. You cannot just use a linear function, or in this case, a line, to be able to separate these two classes, right? So if you use like a linear function line, you can say you can have something like this, but then you have these 0 and 1s mixed on both sides. You can have this, and really you cannot like cut through this, right? So you really need to have this kind of like an oval type shape classifier to be able to solve this problem. And we're going to use a deep learning library in the next video to solve this problem and learn, what type of neural network you can use. But the goal right now is to show you that there exists a very simple neural network model with a hidden layer that you can use to correctly classify these data points. That's the goal here. So I'm going to give you the weights right now, or the parameters of neural network. In general, you don't have those, but right now, let's say you know the correct solution and you just want to verify that. So the architecture is very simple. You have your input layer, which has 2 nodes. You have a hidden layer with 2 nodes, and then the output layer, which has 1 node, again, because this is a binary classification. You can even make this easier if you really want to, don't want to like draw all these like nodes and say that, well, I have, one set of nodes in my input layer, and there are technically 2 nodes here. I have this weight matrix that takes me to the hidden layer, and then another weight matrix that takes me to the output, right? So this 1 and 2 here corresponds to the weights for the first layer, meaning going to the first layer, which is hidden layer, and the weights for the second layer, which is the output layer. So if you want to use the same notation as we used before, so we need to put all these inputs together. So remember, we have 4 inputs here, and each one has 2 dimensions. The way that we did before was that each data point is placed in one column, right? So we have 0 and 0 for data point 1, 0 and 1, 1 and 0, 1 and 1. So it's 2 by 4 matrix for 4 data points. Right now, we know that W1, this weight, given what we just discussed, should be 2 by 2 because we have 2 nodes and 2 nodes. And let's say these are the optimal or correct values. And also we have one bias for this H1 and one bias stem for this H2. And let's say these are the values. And in this case, we also assume that the activation function, or that nonlinear function, is what is known as ReLU, which stands for rectified linear unit. It has a very simple form. It is max of 0 and its input argument. So this means that if z is greater than 0, that's the output. And if it's less than 0, just cut that and map everything to 0. Okay, so let's start by finding the mapping from input to hidden. So this is a ReLU. We have W1 times X plus B1, right? That's the map that we have. So W1 is here. This is the X, the matrix of all inputs. And then we have this bias term. So you can do the first matrix multiplication. That should be easy. You multiply each row by each column, simplify this. Something that you have seen in any kind of linear algebra class. And now we have to just add this bias term. So something to always remember here is that if you have more than one data point, here you have 4 data points. Usually we just write this plus the bias term, but the fact that really matters here is that you actually have to apply these to each column, right? So if you really want to be very mathematically rigorous here, you have to repeat this column vector 4 times and have 0, -1, 0, -1, 0, -1 in all like 4 columns of this matrix so that dimension-wise everything match. But it is very common in the neural network literature to assume that this will automatically get extended, or what they call in a more programming language as broadcasted. And so this 0 and -1 will be applied to every single column, which this is what you get, right? So you add 0 to all the elements in the first row and -1 to all the elements in the second row. And remember, now you have ReLU, or rectified linear unit, and this one is also element-wise. So this means that you're gonna, if everything here, any element that you have here, if it's greater than 0, it's gonna be 0. And if it's positive, you just keep that value, right? So these are the 4 elements you're gonna keep. So let's just recap what happened. So we have these inputs that are 2D, two-dimensional. And now we map them into the hidden layer. So now we have these 4 data points because we have 4 columns. And this is the representation of first data point, second, third, and fourth. And now we pass this through the last part, which is going from hidden layer to the output layer. And therefore, in this case, you can see that we need to have another weight matrix. And this one's going to be 1 by 2 because we have 1 node and 2 nodes. We assume that the bias term is 0, and we don't use any activation function. In general, you want to use a sigmoid or logistic function if you have a binary classification problem. But again, this is a very simplified case. We only have 4 data points, and we just want to show you that it is possible to find a perfect classifier in this case. This is just more like a way of showing the existence of a really good neural network model. And if you do the same thing, now you have to multiply your weight matrix by this, hidden representation. And if you do the multiplication here, this is very interesting. You end up with 4 values. So these are the labels or outputs for each data point. Again, each data point is in 1 column. So we get 4 elements here. And the question is that, did this work or not? And so let's see. So these are the 4 inputs that we have, and these are the 4 outputs that we got. And interestingly, you will see that here, that the first and the last data point, they belong to class 0, and that's exactly what we wanted. And then the 2, like the ones in the middle, they belong to class 1. So we found a classifier in this case that can correctly, with 100% accuracy, classify these 4 data points. So that's the power of neural networks. They are able to extract definitely more complex patterns than just linear models, like linear regression or logistic regression. So we have the full analysis of these here in this slide, where we have all these numbers, all these matrices and vectors. And the only difference here is that instead of putting our neural network in the horizontal orientation, here we use a vertical orientation, but this is good to get used to both ways. So it's exactly the same thing, right? Information flows from the input to the output. Something that we need to discuss here very briefly is that why should we even use nonlinear activation functions? And is it really necessary? The answer is yes. If you don't use any nonlinearities or any nonlinear activation functions, then the first transformation that you have is a simple, matrix vector multiplication or matrix multiplication. And then the same thing will happen to the result of this first transformation up to when you get to your last layer, where assume that here we have L layers. And therefore, all these matrices can be multiplied together, and this is just a simple linear model. So therefore, as you see here, if you don't use any linearities, you just end up with a simple linear model, and there is no way of being able to extract nonlinear patterns. So therefore, you want to use nonlinear activation functions. And the popular cases are sigmoid or logistic function, which has this 1/1 plus e to the negative a. We talk a lot about this when we talk about logistic regression. We know that the output of this always from 0 to 1. So if you're trying to find a probability score as your output, this is great. The other one that you can use for your hidden layers in particular is this ReLU, which is this max of 0 and its input argument. And there are also more recent versions of ReLU too. So again, ReLU stands for rectified linear unit. The nice thing about it, it's its simplicity. It's widely used in deep learning, and it's a nice way of introducing non-linearities into the network. But the main issue here is that everything that is below 0 will be mapped to 0, right? So you're going to lose a lot of information. And this is what is known as the dying ReLU problem, right? Meaning that later when you want to find derivatives, gradients, that can cause a lot of issues with, losing gradients in some sense. So that's why there have been some efforts to change the behavior of this ReLU, especially for negative values of x. One of them is this exponential linear unit, where you can see that for positive values, we have exactly the same thing. But for negative values, now you have this alpha e to the negative 1. Okay. So you see that if x equals 0, right? So e to the 0 is 1. 1 minus 1 is 0. So the nice thing is that this is a continuous function, obviously, which is very helpful. But then the slope that we have kind of like for the negative values or the behavior really depends on this alpha. And this is usually something you define before starting the training process. So it's considered a hyperparameter instead of a parameter because you don't learn this, and instead usually you fix this. Another option is what is known as soft plus, which is a smooth approximation of the ReLU function. And it has this very nice form of log of 1 plus e to the x, right? So for very large values of x, right, so e to the x would be the dominant term, and then log of the e to the x, there are two inverse functions, so it would be x, and that's exactly what ReLU is. So we can plot this by hand, but since we have Python, let's just plot these three functions and see how they look like, right? So that's something that kind of interesting. So let's say our inputs are from -5 to 5, and we have 200 equally spaced points. For ReLU, we define this function, which is the max of 0 and the input x. For ELU, what we use is this np.var, which means that if this condition is true, then this is the output. And if this is false, which means that x is less than 0, then this is the output that we have. And then for the soft plus is log of 1 plus e to the x. And after this, we use these subplots to plot ReLU, ELU, and soft plus. So you can see that in this case, the famous ReLU is just this simple, a stepwise linear function. And then here we are also showing ReLU using this dotted curve here. And you can see that for positive values is exactly the same. For negative values, you have now you let some negative values to pass, right? And then for the soft plus, it's really a smooth approximation of ReLU, right? We don't have this this part here that is problematic when you want to find derivatives, right? Because this is definitely not differentiable, the ReLU part at 0, right? On one side the derivative is 1, on the other part is 0, whereas this soft plus has this nice smooth shape. And for the ELU, for example, you can see here that you can change these values. For example, you can use 1, so you can see that now you don't let as much negative values to pass through, right? And if for some reason you want to put that alpha to be 0, then you get exactly ReLU, right? But let's put that back at something different, because that's the goal, to have something that doesn't suffer from the dying ReLU problem. So just to wrap up what we have, so neural networks, in the simplest case, you can think of them as feedforward models, meaning that you have an input layer, you have information going from this layer to the next layer. You can have more hidden layers, as many as you want, and that's called the depth of the network. Also, you can have more neurons in each layer, which is the width of the network. And then in the last or output layer, you have the number of neurons to be set to the number of outputs, right? So if you have a regression problem, you're trying to predict one output, that's one node. If you have, multiple outputs, use multiple neurons. And for classification problems, if it's a binary classification, you only need one node. And if you need to solve a problem with more than two classes, then you put one node for each class, right? Because then you can use the softmax function. That's why we covered that in a previous video, where you can use multiple nodes in a multiple class classification problem, and use softmax function, and you find probabilities that each data point belongs to one of the classes.